Hello, dear students. Welcome to session 8 in the tutorials of MATH204 offered to business informatics students, semester 2. I hope we have studied what we have discussed before because the topics are related all together. However, today we will start a new topic. Let's first remember that in the last session we have discussed the inverse matrix. And we said that it will replace the division in the matrices operations. And we have discussed a very important property of the inverse matrix, which is its uniqueness. It's, if a matrix is invertible, its inverse is a unique value. So given, if we have a matrix, this is an example for a 2 by 2 matrix. If it has an inverse, let's assume that there is an inverse and it's invertible, then it will be a 2 by 2 matrix as well with unknown elements still. And the definition of the inverse matrix is that its product with its inverse is equal to the identity, is equal to 1, as if we are looking to a number and it's reciprocal, like we are multiplying 8 by 1 over 8. Of course, the result is 1. The same with matrices. If you're multiplying a matrix, this is called B with its inverse, B to the power negative 1. We called here its inverse X. So this production should result the identity matrix with an order or the dimension of the same matrix. Solving this for these unknown values, if we need to get these unknown values, solving for it in general, we will get this production after multiplying these two matrices with our basic multiplication operation, and then equating two matrices of the same size. We know that every element got to be identical to its corresponding one, which means that here this formula is equivalent to 1, and that 1 which exists in row 1 column 2 is equal to 0, and hence we will get this these equations. Solving them, we will need two linear system of equations, one where we will have the x1 1 and x2 1. In the other system we will solve for x1 2 and x2 2. Because of this answers is not all of zeros, then this system is homogeneous or inhomogeneous. Exactly, it's inhomogeneous, and we have the three types of possible solutions, which is unique, infinite, or no solution. And hence, after solving these two linear system of equations, we will get the inverse of B with these values such that x11 is the -7, x12 is the 5, x21 is the 3, and x22 is the -2. In today's session, we will discuss a very important topic, which is the eigenvalue and eigenvector for a squared matrix. A squared matrix, we have discussed it before. It's an n by n matrix such that the number of rows is the same as the number of columns. Let's first discuss what is the eigenvalues. Actually, having this relation for any n by n squared matrix A, if we have a non-zero vector, A is an n by n matrix, and V is a non-zero vector. Let me denote it by the bar. You know, if it's text, in the text we can make it bold, and this indicates the vector, but when we are writing, we have to add this bar or hat above or below. So given that this vector is not equal to 0, this product, if it exists for any non-zero vector, we got the same vector but scaled with a scalar. So if we multiply any squared matrix n by n with a non-zero vector, and the result is the same vector but scaled with a scalar quantity or a constant, in that case we call this vector the eigenvector for the given matrix, and this constant or scalar quantity, the eigenvalue for the given matrix. This is what is the eigenvalue and the eigenvector. Let's get to why do we need it? Why do we need them? Actually, there's many applications where the eigenvalues and eigenvectors arise. The eigenvalue problem, it arises a lot in the calculus and as well in computer graphics. The eigenvectors are vectors which keep its direction. If we transformed a picture in transformation or in matrices transformation, you know that these pictures are stored in our computers in matrices, in a matrix form. So transforming this picture or the screen of your computer, the eigenvector keeps its direction, and this is a very good, a beneficial characteristic. Okay, why the eigen? The word eigen is a German word. It means own or typical. Like you say, das ist ihnen eigen. In German, that is a typical of them. The translation of this sentence is that is typical of them, which means in English characteristic. So we have a characteristic value for the given matrix and a characteristic vector for a given matrix, which can be able to represent this matrix in different situations. Okay, so this is what the eigenvalues and eigenvectors, and a brief idea about why they are very important. How can we do this, or how can we get the eigenvalues and eigenvectors for a given squared matrix? Let's try to do this step by step together. We said that this relation holds if we have a squared matrix multiplied by a non-zero vector, and this is equal to the scaled of this vector. If x is not equal to 0, this means that this vector is called the eigenvector of the a, and the lambda scalar quantity, which belongs to all real numbers, is an eigenvalue for a. Solving for lambda, if we need to get the eigenvalues and eigenvectors for a given matrix A, we are going to solve first for the lambda. Let's get the lambda. Solving this equation for lambda, what shall we do? We will take this term to the other side, and hence, let's remove this quickly. We will get a times x equals, now we took it to the other side directly, it will be lambda times x, and it will be equal to 0. Now let's get x, take it as a common factor. We can take it from any side. So we will have a minus lambda, and x is a common factor, equal to 0. Let's stop here for a moment. A is what? It's an n by n matrix. Lambda is scalar. Can we subtract a matrix from a scalar quantity? This is inapplicable. We know that we can multiply a matrix by scalar, but subtraction and addition is not. So in this case, we will add the identity. To get rid of this trouble, we will add the identity matrix, which is the one of matrices, in order to have two similar sizes matrices and be able to apply the subtraction. Now solving for lambda, this product, if we have this term times the x is equal to 0, and knowing that x is not equal to 0, so from where would come the 0? From this term, exactly. Therefore, this matrix got to be not invertible. It has to have no inverse. It has to be a singular matrix, and singular means what? Means it's, if you remember, means from the last session where we discussed the determinants, its determinant is equal to 0. If the determinant of a matrix is equal to 0, we said before that this means that it's a singular matrix and it has no inverse. So this product comes from This relation comes from this equation. Solving this equation, it's called, by the way, characteristic equation. This is the short of characteristic. It's C and then / CS, like this equation. If we are solving for A minus IN, this is a polynomial of lambda, and it's called characteristic polynomial. So here we have a characteristic equation and a characteristic polynomial. Let's go on solving. Okay. A is given here. If you can see it, it's 2, 0, 0, 2. So it's a 2 by 2 matrix. This is A1. Let's form this matrix. We will have the elements of A minus I, which is the identity, of order 2 times lambda, and then equate this with 0, equate the determinant of this subtraction with 0. Let's apply this scalar multiplication. So we have 2, 0, 0, 2. This is A minus, this identity after multiplying it with lambda is going to be lambda, 0, 0, lambda, scalar multiplication. Let's do this subtraction. Every element subtracted from its corresponding, 0 minus 0, and then 2 minus lambda. And hence, we need to solve for the determinant equal to 0. We remember that the determinant was the product of the two diagonal elements minus the off-diagonal elements. So we have 2 minus lambda squared minus 0, which we can write equal to 0 directly. Now, what's the values of lambda? Solving this equation, applying square root both sides, and then move the lambda to the other side. Lambda will be equal to 2. Now we have found the eigenvalue of the matrix, 2 by 2. That's it. How about finding the eigenvector? We can start working here. How about finding the eigenvector? Let's get back to the equation that arose with us. Here we said that this system is equal to 0. And now we know the lambda. Now the lambda is well known. And of course, the matrix itself is given. The identity is known. What is the only unknown? It's x. So this is the equation which we will use in order to get the eigenvectors. What is this system? What does it describe? If you remember, if you went through your memory, you will memorize that it looks like a homogeneous linear system of equations, right? Where this vector is the unknowns, which were x1, x2, x3, or x, y, and z. And this is the coefficient matrix is equal to 0 vector. This is the homogeneous linear system of equations. Let's go on solving it. A minus lambda. Now we know that lambda, or the eigenvalue, is 2. So we will directly substitute it. 2 minus 2 is 0. And then the 0 will remain. And we have here lambda is 2. So 2 minus 2 is 0 again, 0. If this is a homogeneous system, what does it tell us? We have two unknowns, right? We were looking for a vector x which belongs to R2 because we are dealing with n by n matrix. Here it's 2 by 2. So we were expecting a vector which belongs to R2. Here we have free term. If we were looking for x, y, and this is the equal, it seems that the diagonal element of x is 0, so there is no pivot, and it's not a fundamental variable for the system anymore, and y as well. And this means that the eigenvector, if we called it here x, it belongs to all R2. It can be any vector in R2. So we will say that it's any vector or is an eigen vector of this given A1. If we multiply this matrix, this given matrix A, by any vector that belongs to R2, it will be equals to 2 times the same vector. Try it yourself. Multiplying it by 1 and 1, for example, you will get the vector 2, 2. Taking 2 outside as a common factor, it will be 2, and the vector is 1, 1 again. Try it with all the vectors that belongs to R2, any vector that can come to your mind. It's an interesting thing. The second example here is for another matrix, which will arise different solution. The matrix is -7, 5, -10, 7, and this is A4. If we need to solve to get the eigenvalues, we will directly use this characteristic equation. So A minus lambda, we will subtract the identity multiplied by lambda. So lambda will be in the diagonal and zeros in the off-diagonal elements. Do this subtraction directly, it will get this matrix here, 5 minus 0, and then -10, and 7 minus lambda. This determinant, solve it. If it's equal to 0, we will multiply the diagonal, -7 minus lambda multiplied by 7 minus lambda, and this product is minus the -50, so we can write it directly plus 50. It's equal to 0. Apply this multiplication, we will get lambda squared, and then -7 lambda minus lambda times -7, this is +7 lambda, and they will cancel each other, and then we will finally have -7 times +7, which is -49, plus 50, which is +1, equal to 0. Solving this equation for lambda, we will get square root of what? -1, which means that it's not a real number, so lambda doesn't belong to the real numbers, and if a matrix doesn't have a real eigenvalue, and hence we will decide that it has no eigenvector. So we will say then A4 has no eigenvector. We have seen now 2 cases where here in this example, we had all the vectors that belongs to R2 can act as eigenvector for the given matrix. Here, quite the opposite. This matrix, these numbers formed no real eigenvalue, and hence it got no eigenvector. So we might have the whole space as an eigenvector that fits, and we might not have a single eigenvector. Let's have another nice example. This one. Here we have a matrix which is 3 by 3, B4. It's from our classwork 4, classwork 8, exercise 4, or D. So what are we going to do here? If we want to calculate the eigenvalues and eigenvectors, we will write this characteristic equation, the matrix minus lambda times identity, and its determinant is equal to 0, and we will solve this. This is the whole matrix copied again, minus lambda times the identity. This time it's of size 3 by 3 because of the size of the main matrix. Do the subtraction. The diagonal elements only will be affected. They will be minus lambda because here we multiplied these ones by lambda. The off-diagonal elements are not affected. They are exactly the same. This is how we can signify the diagonal elements. Equate this determinant by 0, which means we can get the determinant here using the Saris rule that we have just discussed in the last session, or using the cofactors where we were choosing a row or a column and go with each element, taking care of the sign, which is called the minor, -1 to the power I plus j, and multiplying it by its cofactor. So here, if we worked, it worked here with the first row. So it's 9 minus lambda. Remove the row and column of 9 minus lambda. You will be left with these 4 values. Get their determinant using the 2 by 2 determinant procedure, which is the product of the diagonal elements minus the product of the off-diagonal elements. And then minus, of course, we will follow the pattern of the sign. Minus 2 times what? Remove the column and the row. You will be left with this 2 and these 2. Get the determinant. Plus 16. Again, remove the row and column of 16. You will get these values. And then we will use this cubic polynomial, solving it using the calculator or algebraic. The important thing is that we can calculate the eigenvalues as lambda 1 and lambda 2. It seems that they are identical, and this is called multiplicity. We have multiple eigenvalues of the same value. So these 3 eigenvalues are not distinct. They are not 3 different values. We have multiplicity for eigenvalue 1 and eigenvalue 2 because they are identical. Getting their eigenvectors, let's do one together. For lambda 1, if you remember, we had the 2 lambdas, 2 identical lambdas, which were 1. So we will work for, we have to indicate for lambda 1 equals 1, and it was the same as lambda 2. So we will work for the first 2 eigenvalues. And then we will work, now we know the value of the lambda, so we will subtract from every diagonal element this lambda value from these diagonal elements. 9 minus 1, this is 8. And then the off-diagonal elements remain unchanged. And then 7 minus 1, this is 6. And 48 as it is. -8 is an off-diagonal element. -2 as well. -15 minus 1, this is -16. Get the determinant. Here we are finding the eigenvector. So we are solving the system. This is the A minus I n lambda. What's the n here? The matrix is 3 by 3, which means it's I3 equal, or this is multiplied by x equals 0. This is what we are solving here. This is the matrix of coefficients that we dealt with before. These are the unknowns which we will get from solving using Gauss. Let's apply the elementary row operations to this form. We will find an output 1 and 1/4, 2 and then zeros. Of course, we remember that for the homogeneous linear system of equations where we have the results are zeros, we have only 2 types of solution. It's either infinite solution or or a unique solution of zeros. And for this system to be functional or working example, it got to have a meaningful solution, which in this case is the infinite solution. Because we have stated before, if we have the unique solution of zeros, this physically has no meaning, and this is why we call the trivial solution. So we expect that we will have this infinite solution. Now let's identify it. The first element in the diagonal is 1, which means it's for a basic variable. We can call it x1, and here for x2, and this is x3. The second one is 0, which means it's a free variable. And we have only one equation, which says that x1 plus 1/4 x2 plus 2x3 is equal to, moving this bar, we turn to the equal to 0. It seems that x2 and x3 are free, so we may keep them as they are and write x1 in terms of them. In this case, it will be negative 1/4 x2 minus 2x3, and hence the eigenvector is composed of x1, x2, x3. This is x1, 1/4 x2 minus 2x3, and then x2 and x3 is the same. This is one way of representing the infinite solution. We might have named x2 and x3 with different parameters, and we will indicate let x2 is equal to t, such that t is element of ordinary numbers. Let x3 equals to r or s or whatever parameter, such that this parameter is element of ordinary numbers, or we can leave them. It's a dummy name, so we can leave them by its names, and we know that we will get rid of it soon. Now we have 2 degrees of freedom, which means we have to separate these values into 2 vectors. Then we have here the coefficients of x2, which is 1/4. We have here 1. Here no x2, then it's 0. The other vector for x3, we have here -2. No x3 here, then it's 0. We have x3 here, which is 1. So we have 2 eigenvectors corresponding to lambda 1 and lambda 2, which is equal to 1. These are the 2 eigenvectors we were looking for. Perfect. For the other lambda 3, it was equal to -1. We will do the same steps. We will subtract it from the identity multiplied by the lambda. Now it's -1, so negative times, and here we were subtracting. It will turn to positive 1s in the diagonals. This will output this matrix, set it in the homogeneous linear system of equations, and seeking a solution for these 3 unknowns. Using the elementary row operations, we will get this reduced echelon form. This is echelon form, or the reduced matrix. So after the elimination, this means that the eigenvectors must satisfy these 2 equations. We have here a free variable, the third term. The first one is fundamental because it has a pivot. The second value has a pivot. The third one, its value is 0. We are seeking now an eigenvector of 3 elements because this matrix is 3 by 3. We have to satisfy these 2 equations. The first one, which is x1 plus x3 equals 0. This output x1 is equal to -x3. The second one, x1 is eliminated. We have x2 plus 3x3 equals 0, which means that x2 is equal to -3x3. And we can put them in a vector form. x1 is -x3, x2 is -3x3, and x3 is the same. We might have called it t as well, as we did before. Let x3 is equal to t, such that t is element of ordinary numbers. And then you have here from this row, this is x2, right? Here x3, and this was x1. Okay, so here it's x2 equal, let's take this to the other side, -3 what? T. And then x1 from row 1, x1 is what? It's negative x3, which is t. Then it's -t. And we will get the same result. x1, its coefficient is -1. x2, its coefficient is -3. x3, its coefficient is 1. And the multiples, which means that the eigenvector which we are looking for is element from the span set of -1 it's only 1, negative 3, and 1, is element from the span set of this vector. So any multiple of this vector, the span set, if you remember, it's the set of all possible linear combinations. If we have only one element in the set, it means that all multiples of this element. So all the multiples of this lambda, we can say as well, let me say, or x is equal to lambda times this vector, such that this lambda, or call it m, in order to make it different from the eigenvalue, so that you are not confused, call it any value c, for example, such that c is element from all real numbers. It can be any multiple of this vector. This is the smallest vector that can represent this, the dimensions of the eigenvector that corresponds to this eigenvalue. Let me see what we have next. That was for this session. Next time we will continue with the eigenvalues and eigenvectors, and we will see how we are going to use it in a different characteristics of matrices. Study well, stay safe, see you in goodbye.